going to start frequency response techniques. We've finished up with our root locus sections and our design based on the root locus. So today we're going to talk mainly about Bode diagrams, okay? Bode diagrams are an extremely common way of looking at a control system or looking at a system and understanding how it responds to a very specific type of input. So far, the types of system inputs that we've discussed have been things like an impulse. So we had an impulse where we had a Dirac delta. We talked about a unit step, which of course was U of t, and we've talked about a ramp input. Okay, so these are all inputs that are somewhat discrete in a sense. Like after the input has changed its value, it's not really going to change it again. So if you have an impulse, you're going to have some big spike in input. Usually it's a force. Some big spike in input, and then once that spike is done, it's gone. If we have a step input, we have one big change in input, and it doesn't ever change again. And our ramp input is just linearly increasing. Okay. Today, however, we're going to talk about sinusoidal inputs. As you can imagine, there are lots of systems that experience sinusoidal forcing. Why do you think that would be? Why do we see a lot of sinusoids in real life?
Is that more closely related to certain maybe like systems you'd see in reality?
Yeah, like what?
Thinking like a hurricane, not hurricane, like a earthquake for whatever reason. Like it's making like a building like oscillate or something.
Yep. Okay, that's a good example. So earthquakes do that. What else does that? What else might cause oscillatory forcing?
Like signal frequencies.
Okay, not quite what I'm getting at. I think a physical system. Yeah. Wind. Okay. Think even simpler. Think back to like the Stone Ages. When we have things that rotate, we have cyclic forcing usually. Sure. We have things that happen cyclically because we have something that is rotating. So if there's some maybe deformity in the wheel, that deformity is going to run along the ground every time it cycles. And it's going to cause an interesting force to happen every time we go through that cycle. Okay, so we have basically anything that rotates is usually going to experience some cyclic forcing. All right, let's see. We can also think about like cam riders. So if you've designed cams at all, you'll have a cam that's rotating, and as the cam passes by a certain surface, that surface might rise or lower, and it will do so every time you go through a cycle of the cam. Okay, so that thing that's raising and lowering due to the motion of the cam is experiencing cyclic forcing. Okay, so we often have sinusoidal inputs to our engineering system. I do have to take a little bit of a step back. I want to make sure that we cover some background information before we go into analyzing these systems for sinusoidal inputs. We need to talk a little bit more about complex numbers and make sure that we are all on the same page about how we can manipulate complex numbers. Okay, so far in this class, we've seen complex numbers. For instance, when we look at values on the S-plane, we've seen things that look like some real value plus something times the imaginary number. Okay, this is what we call the rectangular form. Rectangular form of a complex number. Okay, in rectangular form, things like adding and subtracting complex numbers is fairly easy. So if I have another, maybe we'll call this S1, if I have an S2 that's C plus DI, and I wanted to add these two things, well, I'd simply add the real components and add the imaginary components. Or if I wanted to subtract, I would subtract. So if I wanted S1 plus S2, it would simply be A plus C plus B plus DI. Okay, so in rectangular form, this is good for adding, subtracting. Turns out there's another form. If we rewrite our complex number in the form something like this, if we have a complex number z and we write it as r of cosine theta plus I sine theta, this is sometimes referred to as the polar form. And in fact, we reduce this down to r angle theta. This is the polar form of our complex number, okay? We haven't changed the complex number at all. It's just a different way of representing the complex number. And in polar form, it's very easy to do things like multiply and divide. So this is good for multiplying, dividing. Okay, so if I want to multiply complex numbers, it's very easy in polar form because in polar form, I simply multiply the magnitudes and add the angles. And I'll explain graphically what the magnitude and the angle is. Although you've had some introduction to this when we looked at the pole and zero angles when we were doing root locus. So if we have a pole, or sorry, not a pole or a zero. If we have a complex number, let's say we have a complex number out in the real imaginary plane. Maybe this is the value 2 plus 2i, something like that. The magnitude of this complex number is simply the magnitude of this vector that comes out from the origin. So the magnitude is equal to the length is equal to root 2 squared plus 2 squared, which should be 2 root 2. And then what do you think the angle is? What was that? Yeah, so graphically speaking, the angle of this polar number is this theta here. Okay, so the angle, and if I have legs that are equal in size, what is the angle? 45. Okay, so if I wanted to write this complex number in polar form, I would say that 2 plus 2i is equal to 2 root 2 angle 45 degrees. Okay, so these two things are equivalent. Okay, so now let's go into multiplying two polar numbers. So let's say I start out with, in rectangular form, I have 1 plus 3i, and I want to multiply this by 2 plus 3j or I. We'll call it I for today. Okay, let's first write both of these numbers in polar form. To write the first one in polar form, I need to find the magnitude. So it's going to be the square root of 1 squared plus 3 squared. So I'll have magnitude is square root 1 squared plus 3 squared should be the square root of 10. And the angle is going to be tan inverse 3 over 1, which should give me 71.57 degrees. Okay, so this first number should be root 10 angle 71.57 degrees. Okay, and this second one, the magnitude is what? Wake up your brains. Come on.
Arctangent of 3/2.
The angle will be that.
Wow.
Angle will be tan inverse 3/2, which is 35.78 degrees. But the magnitude is what?
Square root of 2 squared plus 3 squared.
Good. This should be the square root of 14, I believe. 9. 13, you're right. Okay, so in polar form, this is root 13, angle 35.78 degrees. Okay, so if I want to multiply these things, I just need to multiply the magnitudes and add the angles. So this multiplication should be root 10 times root 13, angle 71.57 times 35.78. Oh, plus, sorry. This should be plus. Okay, so it should be root 130, angle 107.35 degrees. Okay, this is going to be important for today. We're going to have to deal with some complex numbers in polar form today. All right. Finish writing that down, and then I'm going to scroll a bit. I wrote too big, so I had to give extra space. Okay, moving on. Okay, so let's go back to this idea of talking about sinusoidal inputs, sinusoidal outputs. So for a linear system, which, we've been dealing with all throughout this class, so LTI systems, linear systems, sinusoidal inputs, if we give a forcing function to our system that is in the form of a sine or a cosine, then the output will be similarly a sine or a cosine with the same frequency. Frequency will stay the same between the input and the output for a linear system. However, the amplitude and the phase angle might change. So graphically, let's look at what that means. So here I have a sine function. I start at 0, I go up to 1, go back down to 0, -1, and back up. Okay? This is what we might call one cycle. And the frequency is how many cycles pass by in a second. All right? The amplitude of this thing is how high you get off of the x-axis, the height of that waveform. And the phase angle is how much this thing shifts left or right. Okay, so if we were to write our sinusoid in the form y equals a sine of bt plus or minus c plus or minus d, so just a very generalized form, these a, b, c's, and d's tell us about how to graph this thing. So a here is the amplitude of the sinusoid. The frequency of the sinusoid is equal to b over 2 pi. What do you think c is? The phase shift. Yeah, that's how much this thing shifts left or right. So c is the phase shift. And what do you think d does?
Offset.
It moves it up and down. Yep, so C moves it left and right, D moves it up and down. So that's the vertical shift. We're not actually going to deal with vertical shift too much for today. But just for completeness, you can consider it. Okay, so this means that if we have an input that looks like this black line, then our output could potentially be shifted in phase and maybe increased or decreased in amplitude, but it will have the same frequency. Okay, so let's see if I can draw that. Let's maybe say this is going to go up. Whoops. I'm trying to draw it increased amplitude. There we go. Something like this. And of course, this is supposed to be more symmetric than it is. Okay, so I was able to shift the output to the right and increase its amplitude, but the frequency stays the same. Okay. For the rest of today's class, we're going to actually represent these sinusoidal inputs as complex numbers called phasors, where the magnitude of the complex number is the amplitude of the sinusoid, and the angle of the complex number is the phase angle of the sinusoid. Okay. So let's look at that a little more closely. So if I have a sinusoid y, whoops, let's not do green. If I have a sinusoid y equals a sine bt plus or minus c, let's not worry about our vertical shift for today. We'll say all of our sinusoids will be centered about the time axis, or the 0. Then if we wanted to represent this as a complex number, we would say that our complex number representing this sinusoid is A angle C. So notice that this doesn't capture the frequency. There's no b over 2 pi here. But why do I not really care about the frequency for today? Yep.
Is it transient response? Is that why?
No, let's look back at this statement here. It stays the same, right? From input to output for a linear system, my frequency is not going to change. So it makes sense for me to look at it in polar form because it only captures those parts of the sinusoid that might change from the input signal to the output signal. Okay, let's look at how this looks for a block diagram. And in fact, we can even represent our system as a complex number if we plug in some frequency for S. I'll make that a little more concrete. Let's say we have an input sinusoid defined as magnitude input with some frequency omega, angle input for some frequency omega. So this will be the polar form of our input sinusoid. I can use this as my input signal. I can write my system as mg omega angle psi g omega. And my output will be some magnitude output omega angle output omega, where this is the polar form of the output sinusoid. Okay, so all we're saying is that we can represent a sinusoid as a complex number in polar form. Therefore, if I have an input complex number in polar form, sinusoid, I'll get an output number in complex form, or sinusoid. Okay, but let's look a little closer at the system. What the heck is this mg and this theta g for a system when I'm used to seeing my system written as some transfer function g of s? So for the system, mg is going to equal the magnitude of our transfer function if I plug in the value j omega for s. Remember, s is a complex number. So if I have a transfer function in terms of s's and I plug in j omega, I'll get a complex number. Usually it'll be a complex number over a complex number because our transfer functions are usually numerator over denominator. They're fractions. Okay. Okay, so that's the magnitude of the transfer function if I plug in j omega. And therefore, phi here of g is the angle of g when I plug in j omega, where g of j omega is simply g of s as s goes to j omega. Just plugging in the value j omega for s. Okay, after we're in this form, we see this block diagram. With any and all of our block diagrams, we know that the output, everything on the right-hand side, is equal to the signal or the input times the system. Same thing happens here, but now we're in polar form. So I can write this as m output. Oh, and notice also that my frequency is the same for all of these. Whatever frequency I have as in the input is the frequency that's in the system, which is the frequency of the output, all the same omega. So m output angle output is equal to m input angle input times mg angle g. And what do we know about multiplying the polar form of a complex number? What do we do? Yep, Josh?
Multiply the magnitudes
Yep.
and add the angles?
Add the angles. Perfect. Very good. And you came in late, didn't you? So you missed the part where I reviewed that. Very well done, Josh. Great. Okay, so let's see. M output omega, phi omega, is equal to mi mg angle psi I plus psi g. Bless you. Me too, apparently. Okay. So this is all well and good. But how do we really analyze these systems? Notice that I've left omega as a variable. Okay? The way that we analyze these systems is not necessarily by picking a single value of forcing frequency, but we actually tend to analyze systems by looking at how the system responds to any value of forcing frequency. Okay? What do we already know about maybe a particular frequency that creates some particular response that may be especially bad? Yeah, we talked early on about the resonant frequency, right? So what, in terms of what we've just covered, what do we know about the resonant frequency? It means that if we force the system at the resonant frequency of the system itself, of the plant, then the amplitude is going to get quite large, right? Okay, so let's see. Let's take a couple notes here. So we often leave omega as a variable so that we can analyze a system's response to a wide range of possible input frequencies. So for instance, we might maybe draw a couple of graphs. And we're going to say maybe we're going to try to see what our system does for a range of input frequencies. So I'll put input frequency on the x-axis. I'm going to draw two different graphs. Let's go back to our earlier note. Let's look at this one again. What are the two things that might change based on the input that I give it?
Amplitude and phase angle.
The amplitude and the phase angle, right? So I want to give my system a range of input frequencies and see what happens to the output magnitude and the output angle. So the magnitude or the amplitude might change, might be attenuated, or it might be increased. And then the phase angle might be changed. So we might have an output magnitude, and we might have an output phase. That kind of makes sense, right? So if I have some natural frequency and I have some, I don't know, normal amplitude, like single amplitude input, the magnitude of the system might be very, very large. The magnitude of the output might be very large for some input frequency. But for other input frequencies, the magnitude might not be very large. It might just be the natural frequency that causes that high amplitude response. Okay, this makes sense. It makes sense that we would analyze a system this way. However, in actual control engineering world, we don't necessarily plot exactly the output magnitude. Instead, we plot in terms of decibels. And you might get a feel for why we're doing that in a moment, but it has to do with the fact that when we do the logarithm, there are certain math rules to using the logarithm of a number, right? So when we multiply two logarithms, it's the same as taking the log of the addition. There's this weird thing with addition and multiplication for logarithms. So we use that to our advantage. So I'll put except we actually use, instead of just the straight up input frequency, we use the log of the frequency, log omega, on the x-axis. And on the y-axis, for the magnitude, we use decibels, which has the unit little d, big B. And a decibel is equal to 20 log of the magnitude instead of raw magnitude. So it might be kind of intuitive that we want to see how does the magnitude and the phase angle change for a variety of input frequencies. But if we make these small tweaks and we say, okay, instead of just using raw input frequency, I'm going to make a graph where I have the log of the input frequency, and I graph this weird log of the magnitude, so I use decibels. What we've arrived at is a very special set of plots that are named after the person who first designed them. So these are called the Bode plots. Okay. So you'll notice on this Bode plot, I have frequency is not on a linear scale. It's on a logarithmic scale. So this is really the log of the frequency. And then on the y-axis for the magnitude, this first plot, it's not just m on the y-axis, it's 20 log m. So these are, in fact, decibels. And the phase stays the same. The phase is in degrees. Okay. All right, so very special plots called the Bode plots or the Bode diagrams. Not Bode, Bode. All right, next we're going to talk about how to draw or approximately draw the Bode plots for some very simple transfer functions. What do you think we actually do in real life if we want a Bode plot?
MATLAB.
We use MATLAB. Yep. So at the end of today, I'm going to show you how to use MATLAB to find the Bode plots. Guess what function it is? Bode. Yeah, it's really hard to remember. Yes. Okay, so let's learn to do it by hand, and then we'll learn how to do it with MATLAB. All right, so consider the following transfer function. Consider the following, which always reminds me of Bill Nye. Consider the following. I wonder if you can find like old Bill Nye on tape somewhere, because I want to show my daughter, because I don't know if they show Bill Nye in school anymore.
You can find it online.
Can you?
Oh, yeah.
Oh, I so want to show her Bill Nye. We'll have to start that soon. She's 1.5.
Is she talking yet?
Oh my God, is she talking? She said piano the other day. She said opposites. She said, what else has she said that's impressive? Quesadilla. She normally calls it dia. Because I don't know, quesadillas are easy. We do quesadillas all the time. And so we asked, do you want more dia? And she goes, more quesadilla. Yeah, she corrected us. It's fascinating what these kids will come up with. Okay, all right, consider the following transfer function. We have some gain k, and we have some zeros. In fact, I don't care how many zeros. We'll go up to maybe k zeros. And then in the denominator, we might have some poles. Perhaps we have a pole at 0, or maybe we have poles elsewhere. And I don't even care how many poles you have. Let's consider the magnitude of our frequency response. You know, it's actually kind of interesting if you think about it. When you are plugging in j omega, remember when we said that if you have a pole that is entirely the imaginary component, what type of behavior does it create?
Oscillatory.
It's purely oscillatory, right? The real component causes growth or decay, but the imaginary component just does the oscillation. So it kind of makes sense here that when we plug in for S, the j omega, we're saying, okay, plug in an input that is purely oscillatory. It's exactly what we're talking about. We're plugging in a purely sinusoidal input. Okay, so if I plug in j omega and I take the magnitude of this response, I'll have something that looks like k and then the magnitude of whatever imaginary number I get for plugging in j omega plus z1 times the magnitude of that second zero.
Would you not already replace S with JW at this step, though?
Yeah, I'm going to write this at the end.
Oh, okay.
Yep.
Thank you.
Magnitude SM. So I'm writing it this way because I want you to see that when you plug in j omega, you're going to end up with multiplying a bunch of imaginary numbers in the top and multiplying a bunch of imaginary numbers in the bottom. But when I'm graphing these Bode plots, I don't actually use just the pure magnitude. I take the logarithm of this magnitude. I take 20 log of this magnitude of g j omega. And so let's review what those weird funky logarithm rules are. Those weird logarithm rules say that if I have the logarithm with some base b of two numbers that are being multiplied, this is the same as adding the individual logarithms. Weird, right? So what this means is that we're going to be able to break up the resulting magnitude into the addition or the subtraction of the contribution of each pole and zero separately. They're going to add and subtract. So that's why using this logarithm, it actually makes the math easier for figuring out what is the total response. Yep.
Question. So how come earlier we simplified to g omega instead of g j omega, and here we're doing g j omega? Or
I don't think we ever did g of omega. I think we did.
or just omega here. Like,
Yeah. So
that's what I meant.
because that's how you go from the rectangular form of a complex number to the polar form of a complex number. So the j is the imaginary number. It's either j or I, either one. And when you change form from rectangular to polar, you just have the m and the phi. And the I kind of goes away. You just are representing it as a magnitude and an angle.
Okay, I got it.
Yeah, so go back up to here. So from this line to this line, we lost our imaginary number. Okay? Okay, and then we also have the division form of this. So what do you think is the division rule? Subtract, yep. Sweet. Thus, I always relish the chance to use thus. Thus, we have, if we take the 20 log of the magnitude of g j omega, I should get the addition of all the zeros minus all of the poles. So I'll have 20 log k plus 20 log whatever I get from the first zero plus 20 log whatever I get from the second zero. And on and on and on and on until I get all the zeros. And then I start subtracting the poles. So minus 20 log, I have a pole at 0, minus 20 log the other pole. And on and on and on and on until you get to all of your poles. Given that I'm plugging in S as j omega. Okay, so the total magnitude response of the system is simply the addition, subtraction of the contribution of each zero pole, respectively. Okay. So this motivates us to look at the response to a very very simple system. We can look at what happens, what is the response for a single pole, and then we'll look at what is the response for a single zero. The idea being that if you have a more complicated system with more poles and more zeros, it'll simply be the addition and subtraction of the contribution of each. Okay, we're not going to get to a more complex system today. We're just going to cover the single pole and the single zero system. Okay, so let's look at drawing the Bode plots for a single pole and a single zero, recognizing that for more complicated systems, we can simply add and subtract the contributions of each term. Okay, wrote that twice because it's so important. It's actually just because I forgot. Okay, Bode plot for g of s equal to s plus a, which is obviously just a single zero. First thing we need to do is always plug in s equals to j omega, and we'll get something that looks like this. J omega is equal to j omega plus a. And the way that we're going to look at this is we're going to play around with different values of omega and see where that puts the Bode plot on our diagram. So at first we're going to play with omega being very close to 0, and then we'll play with omega being much, much, much greater than that value a. Okay, so if omega is very close to 0, what do you think g of j omega is?
0.
Not quite. If omega goes to 0, it's just a. Yeah. So when omega is very close to 0, g of j omega is roughly just equal to a. I have a 0 times the imaginary number j plus a. Can't forget our plus a. So if plus a is a complex number, which it is, it just has a 0 imaginary component. And so if I were going to plot this value a as a complex number on my real imaginary axis, what would my magnitude of this complex number be? Just a. What is my angle? What is the angle that this vector creates with the x-axis?
0.
0. Angle is 0. Okay? So in decibels, I want to take the 20 log of m, which is just 20 log of a. And my phase is 0. Okay, let's look at what happens when omega gets very, very large. If omega is much, much, much larger than a becomes basically insignificant compared to the omega term. So for gj omega, where omega is much, much larger than a, g is basically just the j omega term. And if I think about j omega as a complex number, I have my j omega on the imaginary axis. I just have an omega here. What is my magnitude? What?
Omega.
Omega, yeah. The distance here is just omega. What is my angle?
90 degrees.
90 degrees. Okay. So if I were to write this complex number in polar form, I could also write it as omega angle 90. And in decibels, the magnitude of this number is 20 log of m, which is 20 log omega. Interesting thing about this magnitude, if I am plotting the value like y equal to x, if this were y equals 20 log omega, but instead of just plain x on the x-axis, if I have log omega, this is really just y equals 20x. And we know that on our magnitude plots, on either of our Bode plots, the x-axis is log omega. So what we're going to see is a line that looks a heck of a lot like 20x. So the slope here is 20. Okay, so these are the Bode plots that we get for this single zero system. If you were to plug it into MATLAB, oh, sorry, no, this is not what you would get if you plug it into MATLAB. This is the linear approximation within each of these zones. So the actual Bode plot is going to be a lot smoother than this, but we can look within these regions and approximate the Bode plot as linear within these regions to get an estimate. So what happens is when our frequency is very low, remember we said when frequency gets very, very close to 0, we call this our low, let me write that bigger, low frequency asymptote. And this is equal to this one right here. Is that what we see? Yeah, our plot's up here at 20 log A. Okay, within this region, however, this is what we call our high frequency asymptote. We get this equation here, 20x, or magnitude is equal to 20 log omega. There's a very, very special point at A, which is the value of the 0. This point is called the break frequency. Not necessarily that anything bad happens here. It's not breaking. It's just that this is the break point between the low frequency response and the higher frequency response. That's where the system starts to change its behavior. Okay, let's look at the phase. If we're going to plot the phase, we start out by finding the break frequency, and then we find a spot 1 decade less than the break frequency and one decade above the break frequency. So a decade would be like, here I go down by an order of magnitude times A, and here I go up by an order of magnitude times A. And let's see, when I was at very low frequencies, when omega was near 0, my frequency was 0. So my low frequency response here is a phase of 0. And when I got to a really high frequency, where omega was much, much greater than A, I was at a frequency of 90. So up here, I have the high frequency response. And between these two, we approximate the phase as the line that connects the two. Okay, so here we have the high frequency and the low frequency. All right, I am starting to run out of time, so I'll go a little bit faster for the single zero system, or sorry, for the single pole system. For a single pole, we assume that G is 1 over S plus A. We're going to put a pole at S equals to minus A. First thing I always do is plug in G J omega equals 1 over J omega plus A. And then I look at what happens to our system when omega is near 0, and what happens to our system when omega is much, much greater than A. Well, when omega is near 0, that J omega term kind of disappears. It's roughly equal to 1 over A. And in decibels, this is 20 log M equals 20 log 1 over A. Again, you can always try to draw this as a complex number on the complex plane. This would just be some amount on the real axis, 1 over a. So what is my angle?
Zero.
Just 0. Thanks, Riley. Okay, let's do the other one. What is g of j omega when omega gets really, really big? Well, it overpowers that a term, and I'm left with just 1 over j omega. Okay, if we think about the top as a complex number and the bottom as a complex number, I can write this in polar form as 1 as the magnitude, angle of 0, because it's just on the real axis, and then omega as the magnitude at a 90-degree angle. And when I divide in polar form, I divide the magnitudes and subtract the angles. So this is 1 over omega minus 90 degrees. Okay, you can convince yourself that this is the appropriate response or the appropriate Bode plot for this system. So we do the same thing as before, where I take my low frequency. Actually, keep in mind that these plots are normalized by the value of A, of the pole. So instead of just frequency over here, we have frequency over A. So in the prior graph, I looked for the point A. A was my break frequency, but on this graph, because it's normalized, it's 1. So this is my break frequency. I start out at a magnitude of, wait a second. This is 20 log MA. So this is also normalized by the 1 over A. Yep. So this is a value, it looks like this is at 0, but it's actually at a value of 1, so it's just above 0. So 1 correlates with the 20 log MA. Okay, so low frequency response, high frequency response, and then similarly for our phase angle, our phase starts out at 0 when I'm 1 decade below the break frequency. My phase is at negative 90 when I am 1 decade above the break frequency. And then between those, I connect with a straight line. Okay. As promised, now I'm going to move over to MATLAB. There we go. All right, in MATLAB, let's convince ourselves that the book is correct. So let's draw the Bode plot for a single 0 system. So I do my transfer function the same way I always do. We'll have S plus 5. We'll say A is 5 just for giggles here. And I have a single 0, but my transfer function wants me to give a numerator and a polynomial for the denominator. So we'll just say the polynomial for the denominator is 1. So this is just the S plus A, 0. And I want to draw the Bode plot for it. Here we go. Okay, so notice versus your plot from your notes that it's not a perfectly straight line and then a perfectly straight line, right? What we were drawing was an approximation, but you can see the asymptotes, right? Somewhere along the middle here, this really does look very linear, and it approaches this flat line, and it approaches this flat line on the left, similarly over here. So let's see, where do we suspect the breakpoint is for this graph? If I put my 0 at a equal to 5? I expect it to be at 5. Okay, so how do I read this graph? What is 10 to the 0?
1.
1, and this is 10 to the 1, and there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 indicators. So if I'm going from 1 to 10, I should be counting by ones when I'm in this decade. Okay, so let's find the value for 5. So 1, 2, 3, 4, 5. Is that the dead center of my asymptote in the middle of my phase plot? It looks like it. And then is it kind of the spot where I break away from being flat to being linear? It sure does. Yeah. So that's our break point. We confirmed our break point. We can also look at the slope of this section. We expect this slope to be roughly what? 20 decibels per decade, right? Because we had that y equals 20x equation. So let's see, do we go up by 20 decibels within this decade?
Yes.
Yeah, so I start out by roughly 20, and when I'm up here at the top, and I'm definitely nowhere near that tall, I'm up at 40. So I go up by 20 decibels within this decade, so my slope is 20. So I would say we did a pretty good job of estimating our Bode plot here. We could do the same for the pole. And again, we start out at 0, we end up at negative 90. We've got this linear section that connects the two. We have our 1, 2, 3, 4, 5. That looks about dead center. We've got 1 decade below, 1 decade above. That kind of sets our other asymptotes. Let's see. 1, 2, 3, 4, 5. Wait, nope. 1, 2, 3, 4, 5. That looks to be roughly the break point. I start out at, what was it, minus 20, or no, minus, what was my magnitude? 1 over omega, so 1 over 5. Okay. Looks to be about right to me. Okay. So honestly, if I were to draw a Bode plot for anything other than a single pole or a single 0, I would highly recommend that you use MATLAB. Okay? All right, so coming up in the next class, we're going to talk about using Bode plots to determine stability. We're going to look at, then later we're going to look at using Bode plots to design controllers. So very similarly to the way that we looked at using the root locus diagram, we looked at the root locus to determine the stability and then control design for inputs that were of the form impulse, step, ramp. We're going to do the same thing using a Bode plot now for inputs that are sinusoidal. Okay? All right, that's all I have for you today. Thank you so much for being here. If you came in late, let me get your attendance, so that's going to be almost everybody.